Welcome to the Deep Dive. We're here to cut through the noise, take complex subjects, and really pull out the key things you need to know. Today, we're digging into something super specific, but honestly really critical in industry: stress corrosion cracking, SCC. Specifically, when ammonia is the bad guy. Now, we're not talking about just, slow rust. This is about sudden, sometimes catastrophic failure. It happens when materials break down because of this precise mix of chemistry and physical stress, often microscopic. So our mission for you today is pretty clear. Understand the two main material groups that are vulnerable, get the exact chemical conditions needed for this failure, and crucially, the strategies to prevent it. Okay, let's unpack this.
Yeah, this is absolutely fundamental stuff if you're working with process equipment. Ammonia SCC, it's sneaky. It needs that susceptible metal, right? But it also needs mechanical stress and the right corrosive environment all at the same time. And the tricky part, like you said, is the stress doesn't always come from, say, high pressure during operation. Often it's the residual stress, the internal strain just left over from when the material was made, like from welding or maybe bending or rolling it into shape.
So it's a hidden flaw, almost baked in, just waiting for that chemical trigger.
Okay.
So, first big question. Which materials are we actually talking about here? What should engineers be wary of right from the start?
Well, the sources point to two main categories, and what's really interesting, maybe even a bit counterintuitive, is they fail under almost opposite conditions. First up, copper alloys. Think copper zinc alloys, so brasses, very common. These guys are vulnerable specifically in aqueous streams.
Aqueous meaning
Yeah,
water involved.
exactly. Liquid water that contains ammonia or related ammoniacal compounds. Then second, you've got carbon steel, the workhorse material for tanks, pipes. Carbon steel is susceptible mainly in anhydrous ammonia.
Anhydrous. So basically pure ammonia, almost no water.
That's right. Very, very low water content. So see the contrast. Water present, bad for brass. Water absent, bad for carbon steel. It dictates the risk.
And ammonia, it pops up in more places than you'd think, right? It's not just in dedicated ammonia plants.
Oh, absolutely. It's a known issue across many industries. Sometimes it's just a contaminant that sneaks into a process. Other times it's added on purpose, maybe as an acid neutralizer, perhaps in the form of certain amines, which can break down into ammonia. You find it in cooling water circuits, steam condensate systems, boiler feed water, BFW. It's this trace chemical that can cause some serious headaches.
Okay, let's focus on those copper alloys first. Brasses. We see them a lot in things like heat exchanger tubes. What's the specific recipe for disaster there? It sounds like it needs a perfect storm.
It really does. For brasses, like Admiralty brass or aluminum brass, the material itself is the starting point. The sources are clear. Susceptibility really jumps up once the zinc content gets over 15%.
15% zinc, that's a specific number.
It is a key threshold. But, just having high zinc isn't enough. You need those environmental triggers too, and they're quite strict. First, you need that water phase, obviously, with the ammonia dissolved in it. Second, the environment has to be alkaline. We're talking pH above 8.5.
Alkaline, right.
And third, this is critical, you need oxygen. Now, it's an aqueous alkaline environment, but you still need some oxygen. Even trace amounts, the source says, are enough to get that corrosion reaction going that leads to the crack.
Trace amounts, wow. And the stress needed. For these, say, heat exchanger tubes, does it need a big operational upset, or is just putting the tube in place enough?
Often, just putting it in place is enough. The cracking can happen at pretty much any temperature common in these systems. It's not usually about high operational loads. Think about when you roll a tube into a tube sheet in a heat exchanger. That process, it leaves residual stress, hoop stress, in the end of the tube. That built-in stress is often all it takes for SCC to start once the chemistry is right. When inspectors find it, they'll see these surface-breaking cracks. Sometimes you see bluish corrosion products around them too.
And the path the crack takes through the metal.
It can vary. Sometimes it cuts right across the metal grains, that's transgranular. Other times it sort of follows the boundaries between the grains, which can be weaker spots, that's intergranular. Knowing which one helps confirm, yeah, this looks like ammonia SCC.
Okay, so that's the aqueous threat to brass.
Yeah.
Pretty specific conditions. Now let's flip to carbon steel. Here's where it gets really interesting, because you said the conditions are almost opposite.
Exactly. It's this kind of weird paradox. Carbon steel thrives, or rather, fails, under the anhydrous threat. The absolute critical factor here is anhydrous ammonia. That means ammonia with less than 0.2% water. That 0.2% number, that's like the magic threshold.
0.2%, tiny.
Tiny. If you can keep the water content reliably above that level, you generally inhibit the cracking. but drop below it and the steel becomes vulnerable. And stress, again, is a major player. For steel tanks, steel piping, the focus is often on those high residual stresses left over from welding and fabrication. The sources also confirm that oxygen contamination, even just a little bit of air getting in, makes things much worse. It increases the cracking tendency. Similar to copper, actually, but the way it works chemically is a bit different in the anhydrous environment.
What about temperature? Big storage tanks see big temperature swings. Does it need to be warm?
Well, higher temperatures definitely make the cracks grow faster, no doubt. But lab tests have shown cracking happening as low as minus 27 degrees Fahrenheit. That's minus 33 Celsius.
Whoa, so even refrigerated or cryogenic ammonia storage isn't safe?
Nope, definitely not immune. And the failure point. If we connect this to the bigger picture, it's almost always near welds. Specifically, welds that haven't been properly stress relieved, and the areas right next to them, the heat-affected zones, or HAZs.
Yeah, HAZ.
Well, that whole zone around the weld holds onto that residual stress from the welding process. And the cracks, they almost always follow the grain boundaries in steel. It's overwhelmingly an intergranular failure.
So the welding itself creates the weak spot by locking in stress. Okay, that takes us straight to prevention. If stress is a common thread and these chemical thresholds are so incredibly tight, how do engineers actually stop this from happening?
Yeah, the prevention has to be really specific to the material and the environment. Let's start with copper alloys again, since high zinc is the problem. The simplest fix is just don't use high zinc brass. Specify alloys with less than 15% zinc.
Or just avoid brass altogether?
Or avoid it, right? Often they'll jump to materials that are much more resistant, like copper-nickel alloys. You hear about 90-10 kunai or 70-30 kunai. Those are pretty much immune to ammonia SCC below about 120 degrees Fahrenheit, 50 C, which covers a lot of cooling water and steam systems. And if you need total immunity, the sources say things like 300 series stainless steel or nickel-based alloys. They just don't have this problem with ammonia.
Okay.
But let's say you have to use brass, maybe in steam service where you might get trace ammonia, then the key is controlling that other trigger. Oxygen. Keep the air out. Limit the oxygen, you limit the SCC.
It's amazing how simple that sounds, yet how critical. A tiny bit of air ingress ruining a whole bundle of tubes. Okay, prevention for carbon steel now. You can't always just swap out a massive storage tank for stainless steel. What's the approach there?
For those big carbon steel structures, yeah, stress control is paramount. The #1 most effective thing you can do is a proper post-weld stress relief, PWSR.
Stress relief, heating it up after welding.
Exactly. You carefully heat the structure, or at least the weld areas, to a specific temperature, hold it, and cool it slowly. This lets those internal residual stresses relax. It's definitely a process for big tanks, but it's vital for safety.
And if you just can't stress relieve some massive field-erected tank, what's plan B?
Well, material choice still plays a role. Using lower strength steels helps. Steels with a minimum tensile strength not over 70 KSI, they tend to be less susceptible. But the most common and reliable control in the field is actually chemical. It goes back to that magic number. Add water. Ensure you have a minimum of 0.2% water mixed into the anhydrous ammonia.
Ah, the inhibitor. Just add 0.2% water.
Yeah.
Sounds almost too easy. I sense a catch.
There's a big one, a major engineering trap, actually. It's called phase partitioning. Imagine a huge storage tank. You've got liquid ammonia at the bottom and vapor space at the top.
Right.
Water prefers to stay in the liquid phase. So even if you add 0.2% water overall, the concentration in the vapor space up top can drop way below that critical 0.2% level.
Oh, wow. So the top of the tank that welds up in the vapor space are still vulnerable.
Exactly. Which means you need another layer of control.
Which is oxygen control.
You got it. For these big storage systems, oxygen has to be kept extremely low. Like below 1 part per million, 1 ppm.
1 ppm. That's incredibly low.
It is. Standard practice is using nitrogen to purge all the air out before you even introduce the ammonia. Because if your oxygen level creeps up, even to say 5 ppm, the risk goes way up, even if you think you have enough water in the liquid. That 1 ppm target. It's non-negotiable for long-term integrity.
Okay, that covers prevention. Finally, let's talk inspection. Because, for equipment already out there, you need ways to find this damage if it started. How do inspectors actually hunt for these tiny cracks, depending on the material?
Right. NDE non-destructive evaluation is key. For copper alloy tubes, like in heat exchangers, they'll definitely monitor the water chemistry pH, ammonia levels as a first check. For physically checking the tubes, eddy current testing, ECT, is very common. It uses magnetic fields to find flaws under the surface. And of course, just plain visual testing, VT.
I'm looking for those cracks and blue stains.
Yep. And for specific areas, like where the tubes are rolled into the tube sheet, you might use penetrant testing, PT. That helps find really fine surface cracks.
And for the big carbon steel stuff, tanks, pipes, how do they check those welds since that's the prime spot?
The go-to method is usually wet fluorescent magnetic particle testing, WFMT. You apply it right on the welds and the HAZ. It's great for finding surface or near-surface cracks.
Okay.
Alternatively, or sometimes in addition, they use specialized ultrasonic testing, UT, angle beam UT, like shear wave or phased array. They send sound waves in from the outside to map out any flaws inside the weld. And for really large vessels, there's also acoustic emission testing, AET.
Acoustic emission. Listen it for cracks.
Pretty much. AET uses sensors to listen for the tiny, high-frequency sounds that a crack makes as it grows under stress. It's fantastic for monitoring if existing cracks are active and finding the hot spots.
What strikes me is the damage isn't always neat and tidy, is it? The cracks don't just follow the weld seam perfectly.
No, not at all. Ammonia SCC can run parallel to the weld, or cut across it transverse, or even run at an angle, oblique. It doesn't follow a simple path. That means the inspectors really need to use comprehensive NDE methods, techniques that can find these flaws no matter which way they're oriented relative to the weld. It demands thoroughness.
So what does this all mean? We dove into this very specific failure mode, ammonia SCC, and, well, what we've really uncovered is just how crucial these tiny chemical boundaries are. Managing material failure isn't random. It really does take that perfect storm. The right environment, is it wet or is it dry? The specific contaminant, usually oxygen. And that constant physical stress, often just sitting there from how it was made. The lesson seems to be that every bit of material, tiny brass tube or massive steel tank, has this hyper-specific weakness defined by these razor-thin margins. 15% zinc, 0.2% water, 1 ppm oxygen. Those numbers are safety.
Precisely. This deep dive really highlights how critical those tiny margins are for keeping huge, expensive, and potentially dangerous industrial systems safe. Managing oxygen down below 1 ppm, making sure water content is just right at 0.2%. These systems depend on hitting those targets perfectly. And that brings up a really interesting question, something for you to maybe mull over. In these incredibly complex systems where you have multiple variables that need such precise control, where failure could literally be triggered by 0.2% of water, how do engineers actually guarantee that level of precision, that consistency over the entire life of the equipment, decades sometimes, through all the wear and tear, shift changes, human factors? Maintaining those tight margins year after year, that constant vigilance, that's a huge challenge and maybe something worth thinking about.